It's my pleasure to have Rafael Alves Batista here today. He comes to IFT as a La Caixa junior leader, working on the project Multimessenger Proofs of the High Energy Universe. He did his undergraduate and master studies at the State of University of Campinas, Brazil. He obtained his PhD from the University of Hamburg in 2015. He has held several postdoctoral positions at the University of Sao Paulo, at the University of Oxford, and Radboud University in Netherlands. His primary research activities are in the fields of astroparticle physics and high-energy astrophysics, including cosmic rays, gamma rays, neutrinos, dark matter, and cosmic magnetic fields. His secondary interests include topics as the foundation of physics and astrobiology. He's a member also of the CTA consortium since several years ago, and he's closely working with the CTA group at the IFT since his arrival past October. And today, is going to talk about the phenomenology of high-energy cosmic messenger to prove fundamental physics and cosmology. Whenever you want.
Yeah, thank you. I'm going to take away my mask, and if this thing starts beeping, I put it back again. Okay, so thanks everyone. Thank you, Ernesto, for the introduction. And today I'm going to talk about how to use high-energy cosmic messengers to probe fundamental physics and cosmology. I don't know most of the audience, so I don't know what you are familiar with here. Therefore, I prepared something more introductory. And if I'm going too slow, please just let me know. So the overview for this talk is essentially, we have high-energy cosmic particles. I'll be particularly interested here in cosmic rays, gamma rays, and neutrinos with very high energies. And these particles, they are useful to probe their sources and the media they traversed in the universe. And we can do both astrophysics and cosmology using these messengers. And we can do fundamental physics and particle physics. So this is a two-way street. And this is the structure of the talk today. I'm going first to introduce these cosmic messengers, how they are produced, how we detect them, how they propagate in the universe. Then I'm going to talk a little bit how to probe cosmology. And since I don't have a lot of time, I'm going to only talk about how to probe magnetic fields, cosmological magnetic fields, using these messengers. And then I'm going to talk about how to probe fundamental physics, in particular Lorentz invariance violation, some specific types of super heavy dark matter, and if I have time, maybe deformed relativity and so on. And finally, I'm going to draw the conclusions. So essentially, as I said, the messengers that I'm interested in are mostly cosmic rays, photons, and neutrinos, but electrons, they are an essential part of all this if you want to assemble this model. And how these messengers are produced. Essentially, these messengers, they gain their energy. They are high-energy cosmic messengers because they are accelerated in some way. In the case of cosmic rays and electrons, there is some kind of particle acceleration mechanism taking place in the universe, in astrophysical objects. And this particle acceleration mechanism renders these cosmic messengers with very high energies, with energies, for example, in the case of cosmic rays, as high as 10 to the 20 electron volts. Well, this essentially, this plot here, it's the so-called Hillas plot, and it essentially shows you how to get which kind of astrophysical objects can accelerate cosmic rays up to very high energy. So if you look at these lines here, you see that the horizontal axis, it shows the size of the object, the vertical axis shows the magnetic field strength, and the acceleration is an electromagnetic process, and therefore you need to have objects with a given size that it's large enough to, and with a strong magnetic field, so that it can contain these particles for long enough, for several cycles, so that these particles can be accelerated. What about the neutral messengers, in this case, photons and neutrinos? Well, these neutral messengers, they are usually produced through secondary interactions, whether photohadronic interactions, photonuclear, and several other types of interactions, usually initiated by the high energy messengers, cosmic rays and electrons. So these are directly accelerated. The neutral ones, they are the byproduct.
Could you share the screen for the people in Zoom?
Ah, I thought it was, yeah, sorry. Okay. Just a second. Can you see it? Okay, I hope.
Thank you,
Yeah.
yes.
No, me está siguiendo.
Okay.
The camera is following me, I think. Now.
Okay, so you come here and then now the camera comes towards
No.
you. Yeah, now you go away. Yes, I think so. Okay. I hope it's okay now. Yes. So, okay, I already went through this slide. And essentially, if we are talking about those messengers that I mentioned in the previous slide, we have here the landscape of all these messengers at high energies as we observe them from Earth. Here it's the measurements observed by ultra-high energy cosmic ray experiments at energies of 10 to the 9 GeV or 10 to the 11 GeV. So these are the gray dots. We also have in orange here, the measurements by the Ice Cube Neutrino Observatory of neutrinos with PV energies, more or less. And we also have the gamma ray background as measured by the Fermi-Lat satellite. And this is interesting because it connects all these different messengers within a single plot. And as I mentioned before, there are some interactions that leads from one of these messengers to the other. So there are some intrinsic connections between these three messengers, which allow us to explore, using the multi-messenger approach, their physics. So some kind of common physics that might generate neutrinos and gamma rays from cosmic rays, for instance. And these messengers, they are usually detected using several techniques. At this very high energy that I'm talking about, usually they interact with the atmosphere. So if we have a cosmic ray entering the atmosphere, it interacts with the nitrogen in the air, inducing an air shower. And this interaction usually produces fluorescence light, which can be detected directly by fluorescence detectors. There are also satellites observing this fluorescence light. Actually, there are no satellites observing fluorescence detectors, but this is a planned experiment. And there are several other particles produced in the shower, including neutrinos, muons, and so on. And they reach these particle detectors here at Earth. And by triangulating the signal of several particles detected by the different detectors, you can reconstruct the properties of the primary cosmic ray. So this is relatively, it's difficult to do, but nowadays we have several techniques to do that. And during this process, during the cascade, there is also radio emission. And gamma rays, they can also be directly detected by satellites, and they can also produce air showers in the atmosphere in a very similar fashion to the one I've shown here. And in this process, Cherenkov light is emitted, which can be detected by, these ground-based satellites like the Cherenkov telescope array. And how these cosmic messengers propagate. So this is one of the main points that I'd like to talk about today, because this is how we are going to extract some information about fundamental physics and cosmology from these messengers. Well, this is a very simple cartoon picture to show how these messengers propagate in the universe. So we have a given source of these messengers, whatever it is. We have the Milky Way, we have Earth, and there are also magnetic fields in the galaxy, outside the galaxy, and so on. And what happens is, if we have a cosmic ray, which is essentially an atomic nucleus, it moves in the universe, it's deflected by magnetic fields, but it can also interact with the photons that pervade the universe, like the CMB, the cosmic microwave background, and also the extragalactic background light, the EBL, and also radiation in other frequencies. And these interactions, they can produce secondary nuclei. And if we have, for example, one of these nucleus or even a proton simply, there is the production of neutrinos and photons, which I'm going to call cosmogenic neutrinos and photons. The photons are shown here in pink or purple, and the neutrinos are shown here in green. These establish, again, a connection between these different messengers, so that if we observe a cosmic ray, you can try to falsify, to test these models by looking at the corresponding gamma ray and the corresponding neutrino signal. what happens now? I've talked about the cosmic rays. What happens with the high energy photons or the high energy gamma rays that I'm interested in? Well, usually they can produce electron-positron pairs, which can be split depending on the magnetic field in between. And these electron-positron pairs, they can upscatter, for example, CMB photons to high energies, and that's effectively what we detect here from Earth. And this process may occur several times. So this whole thing here, it's called an electromagnetic cascade induced by a gamma ray. And in the case of neutrino, unless there is some new physics that we are not very familiar with, they just zip straight to Earth. They don't interact with things in between. And in general, if we want to build models using these different messengers, you can follow a very simple recipe for the propagation. And this recipe is fairly simple. We start with the astrophysical inputs, which tells us what's the energy distribution of these particles in an astrophysical source. Which type of particle we are talking about. In the case of cosmic ray, it's the composition of the cosmic ray. In the case of neutrinos, it's the flavor of the neutrino. And this source, it might be just one, or it might be several sources, and it might change with the history of the universe, with cosmological evolution, and so on. And once we have these astrophysical inputs that tells us about what is happening in the source, we also have the propagation. And the propagation takes care of what's happening in between. So these interactions that I mentioned between the high energy messengers, cosmic rays, photons, and so on, with the CMB photons or with the extragalactic background light, these particles, they may also be kicked by crossing some astrophysical jet, for example, gaining energy. They can also interact with matter fields or the gas that pervades the universe, and they can also interact with magnetic fields, which is one of the things that I'm going to talk about today. And from that, we have the outputs of this very simple recipe, which are essentially the energy spectrum of these particles, as measured here at Earth, the composition or the flavor in the case of neutrinos, the arrival direction of these particles, and the arrival times of these particles. And these outputs is what we effectively combine. It's what we effectively confront with the observations, okay? This very simple recipe is what we usually use if we want to probe these things that are happening in between. If you want to probe photon fields that are present in the universe, if we want to probe magnetic fields, or particle interactions is what we have to change if we want to test other types of, for example, deviations from special-relativistic kinematics. That's what we should change. Okay. Oops. Okay. So now about magnetic fields, which is one of those ingredients. This shows the view of the cosmic web. So the cosmic web is essentially composed by clusters of galaxies, which are these green regions here. And you see these purple, pinkish filamentary structures connecting the clusters of galaxies. That's the so-called filaments. And you see that most of this video, it's black. That's because most of the universe is empty. Those are the cosmic voids, the region in between the filamentary structure, the clusters, where the density of matter is low. And the magnetic field in the universe, well, we know there are magnetic fields in our galaxy and so on, but we also know there are magnetic fields in clusters and in the filaments. What about the voids, the empty regions? Are there magnetic fields there? And that's a very interesting question that I'm going to focus, especially in the context of cosmology later on. But if you just calculate the cumulative distribution of magnetic fields in this cosmological volume, so, you know, this is just the cumulative distribution or the inverse cumulative distribution of magnetic fields with a given strength, you see that several models, they predict very different things. So we don't really know anything about magnetic fields in the universe, essentially. You can just compare all these lines. They all predict very, very different things. But what we do know is that magnetic fields in clusters, they are stronger than more or less 10 to the minus 7 Gauss. In filaments, well, this is not really well measured, but we believe they are somewhere in between 1 nanogauss and 10 to the minus 7 Gauss or so on, and so on. And magnetic fields in voids, they should be less than 10 to the minus 11 Gauss, more or less. The second of those ingredients that I mentioned to perform the propagation of particles in the universe is cosmological radiation fields. We do need to understand them. The CMB is really well understood. It's this dotted line. But the EBL, the extragalactic background light, which comprises more or less infrared and optical frequencies, there are several models here. So this is not really well known. and also the radio background at lower energies. And these photons that compose these backgrounds, they are target photons when we are modeling the propagation of cosmic messengers. So any type of interaction that we want, any type of model that we want to build, any type of interaction that we want to describe, we need to use these as ingredients, and they are all model dependent because we don't know these messengers very well. Okay, and if we are talking first about ultra high energy cosmic rays, so then I'll go to gamma rays and then to neutrinos. Let's start with the cosmic rays. So cosmic rays, they can undergo several types of interactions, and the typical mean free path for these cosmic rays propagating in the universe, it's shown here in the vertical axis as a function of the energy of the cosmic ray. And just note that these cosmic rays that I'm talking about here, they have energies way beyond the LHC. So this is where we can actually probe some kind of physics beyond what current particle accelerators can do. So at much higher energies. And let's take a look here at what happens with the mean free path of these different particles. So protons, helium, nuclei, nitrogen, and iron as a function of their energy. Well, this process here, photon pion production, it's essentially the interaction of a proton with a background photon. Usually this is the CMB, shown here in the red line. And what happens is that the universe is kind of transparent to protons with energy below 10 to the 19.5 or 10 to the 19.6 more or less. And then as the energy increases, there is this strong suppression here. And this suppression, it's called the GZK cutoff. You might have heard of it before. Many people who are doing some kind of studies of Lorentz invariance violation and other kinds of study using cosmic messengers, they talk about the GZK cutoff, which is essentially a proton interacting with a CMB photon. It's supposed to produce this signature here, which we might see or which we might not see. There are also other processes that affect nuclei and also protons, of course, which is just hydrogen, which produces electron-positron pairs. We also have the photodisintegration of heavier nuclei and so on. And essentially this plot tells us how far we can see in the universe using these messengers. And let's take a closer look at the GZK cutoff. So if we essentially do a very simple calculation of the center of mass energy squared here, using that the CMB energy of a CMB photon, it's about 0.6, 0.7 milli-electron volts. We get that this cutoff should be around 6 times 10 to the 19 electron volts for a proton, which means that if we see a proton with energy, let's say 10 to the 20 or at 10 to the 6 times 10 to the 19 electron volt, it should come from relatively nearby. Otherwise, the CMB, we cannot see further than that because the CMB will have attenuated this flux. And in the case of photons and electrons, we have simple processes like pair production and also inverse Compton scattering and their higher order counterparts, depending on the different types of photon backgrounds that we have present in the universe. And if we look at pair production here, what we see is that photons with an energy higher than 10 to the 14 electron volts, they cannot travel more than 1 or 10 megaparsec or so. Here it's in units of the inverse mean free path. Okay, and if we put all this together, we can see that the universe is opaque to the propagation of these different messengers at different energy ranges. And if we start seeing a lot of photons with 10 to the 15 electron volts, and they are associated supposedly with an extragalactic source, what does that mean? Well, that means that the physics that we know is probably going wrong somewhere. There's something wrong with the kinematics that we are using to model it, because photons with 10 to the 15 electron volts, they should not travel more than a few megaparsec. If it's associated with a source at 10 megaparsec or 100 megaparsec, there's something wrong with the kinematics. So that's an opportunity for new physics. Well, and how do we model the propagation? I presented this before, and we have to combine all these ingredients together. Of course, we have to base ourselves on models, as I mentioned before. And if you're concerned not with the observations, but only with this first to do the modeling, we should try to model all the messengers, neutrinos, photons or gamma rays, and cosmic rays self-consistently. And we need to scan the full parameter space of uncertainties, including magnetic fields, the photon backgrounds that I've been talking about, and so on. How to do that? Well, that can be done using a simulation framework like this one, CRPOPA, which is a public available Monte Carlo code that many people have been using for multi-messenger astrophysics, but it has also a very a good potential for being used for fundamental physics studies due to its modularity. And it can be used for several things. Here, just shamelessly spamming you with the code that I helped develop. So there are several possible applications and much more, which includes the propagation of neutrinos in the universe, magnetic field constraints in the universe, propagation of neutrinos in galaxy clusters, tests of ultra-high energy source models, cosmic rays in the galaxy, and so on. But what I would like to stress here is essentially that CRPOPA, it's very flexible and very powerful in the sense that it can handle electrons, photons, neutrinos, cosmic rays. All the main interactions are already implemented. But what you can do is, if you have a hypothetical particle that you are working with, or some kind of dark matter candidate, or so on, you can just add to the code your new type of particle. And if you know the kinematics, you can just, in a similar fashion to these circles here that you are seeing, you can just implement those interactions, and you can do a full multi-messenger study of your new type of particle. And okay, the title of this talk is High Energy Cosmic Messengers as Probes of Fundamental Physics and Cosmology. I'm going to start with the cosmology part, talking first about magnetic fields. Well, we know there are magnetic fields in galaxies. They have micro-Gauss strength. And in order to explain these fields, this micro-Gauss field in galaxies, we need some kind of pre-existing seed magnetic fields. Why? Well, the divergence of the magnetic field is zero, right? Essentially, and if we start doing all these simple electromagnetism considerations, it's very hard to get magnetic fields out of nothing. And if we want to explain this, we need seed magnetic fields that would exist during the formation of structures in the universe. And then some kind of dynamo can amplify these magnetic fields via this term here. In the equation, this is not really relevant for what I wanted to say. But the real question here, and this is the connection with the cosmology or really the early universe, is how did the seed magnetic fields in the universe originate? There are essentially two classes of models to explain that. One says that they originated to some kind of astrophysical process, like a Birman battery, in which you have a pressure gradient giving rise to, within a plasma of charged particles, giving rise to a magnetic field, or some kind of cosmological origin, in which a global process taking place in the universe, in the very early primordial universe, generated these magnetic fields. And here, there are several processes, like these seed magnetic fields in the early universe. They could have originated, for example, through inflation or through some kind of symmetry breaking. So the phase transition, the electroweak phase transition, and so on. And some fundamental questions regarding these magnetic fields is, how were they produced? This is the main question. We don't know how magnetic fields in the universe originated. We don't really know how strong they are, although we do have some constraints. Oops. We don't know their exact power spectrum, so their distribution across different scales. And we don't know their exact topological properties. And of course, these magnetic fields, they are very important for the evolution of the universe, but we don't know exactly what kind of role they played in the evolution of the universe itself. And I'm going to talk about intergalactic magnetic fields. If you recall that video that I've shown earlier, the empty regions, the cosmic voids, I said before, we don't know if there are magnetic fields there or not, although probably there are. If there are magnetic fields in the voids, then the magnetic fields got there through some way. Either they were expelled by some kind of structure, for example, jets of galaxies could have contaminated the voids, giving rise to those magnetic fields, but that's extremely unlikely because there is no time for that over the history of the universe. The second possibility is, if the empty regions of the universe, the voids, have a non-zero magnetic field, these magnetic fields, they originated through some kind of cosmological mechanism in the very early universe, and they are there essentially unaffected by the formation of structures, which is very nice, because then if we can study intergalactic magnetic fields, that's offering us an opportunity to look directly into the early universe, into the seed magnetic field at the very early universe, which grew undisturbed by structure formation processes. Okay, two quantities characterize magnetic fields in general: its coherence length and its strength. Of course, there are others, but to first order, I think it's enough to talk about the magnetic field strength and its typical size. And when I talk about intergalactic magnetic fields, I'm focusing more on these magnetic fields on the voids, because the voids, they fill most of the volume of the universe anyways, as you saw in that video, right? Everything was black, essentially. So they essentially dominate, and when I talk about IGMFs, I'm talking about magnetic fields in the voids, and that's of cosmological interest. There are some constraints on these magnetic fields. So they should be larger than 10 to the minus 12, more or less, in terms of the scale they act. And they should be smaller than the size of the universe. And they should be stronger than these limits that we have from the Zeeman effect. And there are also some other theoretical constraints from magnetohydrodynamics in the early universe, which constraints excludes this region of the parameter space. And the observation of Faraday rotation from extragalactic objects, usually in the radial band, it constrains this part of the parameter space. The CMB spectrum and the CMB anisotropies, it constrains some other part of the parameter space. And now there is this gamma ray cascades. I'm going to talk about this later on in the next slide, but gamma ray cascades in the intergalactic medium, they can be used to constrain these intergalactic magnetic fields. And we are still left with a very large parameter space between 10 to the minus 11 Gauss and 10 to the minus 16 Gauss, more or less. And we are talking about between 10 to the minus 6 megaparsec up to 10 to the 3. So 9 orders of magnitude here and 6 or 7 orders of magnitude in magnetic field strength. So this parameter space is huge. How to better constrain this parameter space? Well, the bottom band that I've shown before, it's the gamma ray cascade band. Usually, gamma rays are used to constrain magnetic fields, intergalactic magnetic fields, using that very simple scheme that I presented before. You have a given source, like a galaxy emitting high energy gamma rays, and these gamma rays, they propagate a given distance, producing electron-positron pairs. In the absence of magnetic fields, these electron-positron pairs, because we are talking about very, very high energies, they would be produced essentially in the same direction. So electrons and positrons, they would be very close to each other. But in the presence of magnetic fields, there is an opening angle here. And then these electrons and positrons, they can upscatter photons from the CMB, for example. And this is what we effectively detect here at Earth. And the strategies for detection is the following. Well, if we have a point-like source, if this effect didn't take place, a point-like source would appear just as a point in the sky, right? But if there are magnetic fields, what's a point-like source will appear extended. So if we have a stronger magnetic field, like 10 to the minus 15 compared to 10 to the minus 16 Gauss, we have the spread of gamma rays here around the position, the central position of the source. And the stronger the magnetic field, the larger this spread in gamma rays. So we can use gamma ray telescopes to constrain magnetic field strength. The second consequence is, of course, if we have these halos, if we have gamma rays traveling across this hypotenuse here, there are time delays compared to the straight line propagation. And the third consequence is that there are effects on the flux of gamma rays that we see from this type of sources. So the stronger the magnetic field, so the black line here, it's in the absence of magnetic field, and the stronger the magnetic field, the lower the flux at these energies here of GeV or so. This is for one particular type of source, but it nicely illustrates what happens with when you have a strong magnetic field. So the strong magnetic field will, of course, spread all those gamma rays in a very large angular window such that we cannot detect them, or at least they cannot be directly associated to the point source. This is the usual strategy. And if we recall this plot, the constraint plot that we have before, and we try to make a new one using the different strategies that we have, well, if we are looking for the extended emission around a point-like source, the size of this extended emission, like 0.1 degree or 1 degree, will give us some constraints on the magnetic field. Okay, if we see, or actually if we don't see those halos around a point-like source, we can constrain the strength of magnetic fields depending on the size of this angular scale. Another thing that we can do is use the time delays. If we have a burst, we know that a bunch of gamma rays were emitted around the same time window. What happens is that we expected them to arrive more or less at the same time, but they don't. Why? Because of the magnetic fields in this case. And we can constrain a different region of the parameter space using these time delays. But these time delays, they are quite interesting in the sense that the time delay that we are talking about, it's between a photon that would travel straight from that source to Earth with respect to the secondary photons produced during the cascade process in the intergalactic medium. There is another way to do this. We can use another messenger. We can just look, okay, let's suppose that there is a neutrino burst somewhere, and this neutrino burst also emits gamma rays with very high energies. Therefore, based on that, we can try to constrain magnetic fields using time delays between gamma rays and neutrinos. And because we don't have many high energy neutrino sources in the universe, which could produce both gamma rays and neutrinos, except for this TXS here, we can only use this one for now. I don't know if you've heard, a few years ago, I don't know what you work on, but a few years ago, this was a very big result. So the ICE-Cube Neutrino Observatory and several observatories across the whole electromagnetic spectrum observed electromagnetic radiation and neutrinos coming from the direction of this blazer. This is an active galactic nucleus. And as you can see here, this is the gamma ray observations in the GV band. This is in the TV band. And the fluxes, they are shown here. The black dots, they show the fluxes according the neutrino fluxes here. It's the electromagnetic radiation. And as I said, we can use the time delay between the neutrino signal and the gamma ray to constrain magnetic fields. And that's a novel multi-messenger method. So we can use these two different kind of messengers to do the same kind of study, magnetic fields, even though neutrinos are unaffected by magnetic fields. And this allowed us to derive the first ever constraints on the coherence length and the magnetic field strength of intergalactic magnetic fields together. And the strategy is very simple. We have the high energy gamma ray flux measured by the observatories, gamma ray observatories at Earth. We fit this flux to infer the properties of the gamma rays emitted by the source. And then we compute this flux within a given time window, and we compare this time window with the time with the neutrinos. So how much time after the neutrinos were detected did these gamma rays arrive? And using this very simple strategy, we could constrain the magnetic field to be around 10 to the minus 14 and part of the coherence length parameter space of intergalactic magnetic fields. Okay, so this drastically improved our constraints on intergalactic magnetic fields. Okay, I should probably skip this slide, otherwise I won't have time to talk about everything. So one thing that we can do with the Cherenkov telescope array, which is a gamma ray observatory that some people here at IFT, including myself, work with, it's actually being built in the Canary Islands. And one thing that we can do is use gamma rays detected by the Cherenkov telescope array when it's built to constrain intergalactic magnetic fields. So if we take, for example, a given gamma ray source, if we just simulate it, we can estimate the significance of detection of magnetic fields with a given strength with CTA, and we can see that magnetic fields with 10 to the minus 13 Gauss, for example, it can be constrained with 6 or 7 sigma. In this case, CTA would be able to strongly limit this parameter space available for intergalactic magnetic fields, which is very interesting. And now it's the second part of the talk, which is about the fundamental physics, how to use all these messengers to study fundamental physics. And we can do many types of study using that. So by looking at the energy spectrum or the arrival directions or the arrival times or the flavor or mass composition of the particles that we're talking about, we can study heavy relics produced in the early universe. We can study dark matter, magnetic monopoles, and we can do many things by just changing the kinematics of propagation of those cosmic messengers. Well, what we have here is essentially a cosmic messenger using that very simple strategy that I've talked about. We have a cosmic messenger, we have a target. In the examples I've talked about so far, this target is a photon, for example, from the cosmic microwave background. And we can just, calculate the center of mass energy squared. And then based on that, we can calculate the mean free path for a cosmic messenger in a background composed of these target particles. And the mean free path, it's very simple. It takes as arguments the distribution, the energy distribution of this target field, photon field in the case that I was talking about, the center of mass energy, the mass of the messenger, the cross-section for this process. And what's interesting is that there is a threshold energy here, which tells us that this process, this interaction only occurs above a certain energy threshold. And if we start playing with this threshold, we start changing the transparency of the universe to all these different types of messengers that we are talking about. What does that mean? Well, as I said earlier, if we change the transparency of the universe, let's suppose that we, as I said before, we don't expect to see gamma rays with 1 PV energy coming from farther than 1 or 10 megaparsec. If we see a gamma ray associated with a source at 100 megaparsec, something must have changed in this equation. Probably the thing that changed is this, the threshold energy for this interaction to occur. Okay, and we can simply write this threshold energy. And this threshold energy is sensitive to new physics, to whatever you want to do. One of the things that it's sensitive to, it's Lorentz invariance violation. So this is the previous slide. And if we just write down the dispersion relation for the energy of one of these cosmic messengers, identified here as I. So the energy squared of this messenger, it's the mass squared. This is the usual part that we are all familiar with. But we can start playing with another small contribution coming, for example, from a Planck-scale, or actually the scale at which quantum gravity effects, depending on what you want to test. The scale at which these quantum gravity effects kick in. And that will modify this dispersion relation, leaving very clear imprints in the mean free path of these cosmic messengers. So this is a very good way to probe fundamental physics and to probe things at energies way beyond what we can reach with the LHC, for instance. And what's also interesting is that these small effects here, in principle, they are small, of course, but if we're talking about a messenger that leads to a cascade process, this effect will accumulate over long baselines. Therefore, cosmic messengers are a very powerful probe of fundamental physics like no other at the moment. Let's take a look at Lorentz invariance violation in the photon sector. So we have the usual pair production, Bright-Wheeler pair production process, in which we have a high energy gamma ray interacting, for example, with a photon from the CMB or the ABL, the extragalactic background light, producing a pair. In this case, we can simply write the dispersion relation in this way, and where n here, it's the order of the Lorentz invariance. And what happens is that I said before, this is how you calculate the mean free path. The mean free path tells us about the transparency of the universe. One of the things that we can change is the cross-section. So by doing that, we start changing the cross-section for this Bright-Wheeler process. If we take a look at the black line, the black line tells us what happens in a Lorentz invariant scenario. So this is what we're used to. And if we start using different values of the scale where quantum gravity effects kick in with respect to the Planck scale, we start to see some deviations in this cross-section for pair production. This is the superluminal case in which this term is positive, and we also have the subluminal case in which this is negative, and so on. And effectively, the other thing that changed is the threshold energy here in epsilon mean. And epsilon mean, if you write this in the vertical axis as a function of the photon energy, this is what we get. We get this dotted line, this dashed line. It's the standard Lorentz invariant scenario as a function of the energy. But we start to see strong suppression, strong changes in the threshold energy for pre-production to occur. And again, this implies changes in the transparency of the universe to this messenger. And Lorentz invariance violation studies is one of the things that we can also do with CTA. For example, if we take the case of Lorentz invariance violation with n equals 1, recalling that n is just the order of the violation, or n equals 2, we can see that we can very well describe, we can observe this type of effect with CTA. So if we have like observations with these black dots of a given astrophysical object at a given energy scale, what we see is that if we start considering Lorentz invariance violation at a given energy scale here, this spectrum will start to go up again. And that's very interesting compared to the absence of Lorentz invariance violation, because that means that we will start observing things that we should not be observing within the default picture of normal special relativity. And in the cosmic ray sector, and I'll probably finish very soon because I'm running out of time, but in the cosmic ray sector, we can take a look at the photon pion production again. And the photon pion production, essentially, if we look at the attenuation length, this is kind of the mean-free path, not exactly, but you can think of it as a mean-free path, just think of it, but it's not the same, okay? And what happens is that in the absence of Lorentz invariance violation, we have this black line, and this line, as we start including Lorentz invariance violation in this photon pion production, the stronger the Lorentz invariance violation, the higher this curve will be, meaning that this messenger will travel will be able to travel much farther than in this other case. We can also do the same thing for photon disintegration, taking, for example, the iron nucleus and calculating the photon energy in the rest frame of the nucleus. So this is the case, Lorentz invariant case. And if we start including Lorentz invariance, we get this family of curves. And we can do this type of constraint using also the Pierre Roget Observatory, which is an observatory with like these particle detectors, as I mentioned in the beginning, in Argentina. There are like 3,000 of these water Cherenkov tanks and so on. It's very big, but I won't talk about it now because I don't have time. But what we can do is we can take the observations by the Pierre Roget Observatory, which are these black circles here. So when you observe cosmic rays, we have the spectrum, but we also have the composition of these cosmic rays, right? Because what we see here at Earth is not the primary particle arriving from space. What we see is the shower, and we have to reconstruct. Therefore, this is what we effectively see in terms of composition. And if we fit the spectrum of cosmic rays arriving at Earth and also its composition, and if we compute based on this type of processes here, you see that the decay of the pion produced via proton interaction generates gamma rays. Here we have electrons that generates gamma rays, and so on. And if we put all this together, we fit the cosmic ray data and we compute the flux of photons produced by the cosmic rays there. Well, it's disappointing. It's well below the limits here. We cannot tell anything. But if we just change, if we start taking another scenario here that also fits the data with just a chi-square slightly different from this one, we can start changing things. We can start excluding some Lorentz invariance models. In this case, the black line is the case without Lorentz invariance violation, and we can exclude part of the parameter space of Lorentz invariance violation, like we did in this very recent work here. So this minus 10 to the minus 21, for example, it's excluded for n equals 0, the order 0 of Lorentz invariance violation. And the same for n equals 2, we can exclude part of this parameter space and so on. And using, this is the integral flux of photons that we would expect. These are the upper limits, right? This is for Lorentz invariance violation. But the non-observation of photons with these energies by the Pierre Roget Observatory would also allow us to constrain, for example, models of super heavy dark matter, which are these pink lines here. We would expect, according to these different models, this number, this amount of photons that would result from the decay or annihilation of super heavy dark matter, and the fact that we don't see any photons in this energy range with the Pierre Roget Observatory constrains some of these models. And I won't have time to talk about this, so I'll just go to my conclusions. As I said, high energy cosmic messenger are exceptional probes of cosmology because of their long baselines and high energies, and they can be used to probe intergalactic magnetic fields, which is very interesting because that provides us a window into the early universe. And high energy cosmic messengers, they are also useful to probe fundamental physics because they can amplify quantum gravity scale or Planck-scale effects. And we can actually use them to constrain Lorentz invariance violation much better than what we can do with Earth experiments. And I didn't have time to talk about this, but deformed relativistic kinematics. And yeah, essentially the multi-messenger framework, it's very powerful because we start combining multiple messengers in one, and they offer complementary information to each other, and our constraints are going to be much better within this framework and much more reliable. And that's all I had to say. Thank you.
Well, thank you very much for your nice seminar. It's time for questions and comments. Here or by Zoom, no problem.
So there is something I didn't understand in your slide 20. Which is that,
Oops.
that one.
Yeah, it's
That's right.
okay, this.
Yeah, which is when you explain the gamma ray cascades.
Mhm.
And I'm struggling to understand why the orange region is the area that you're
So
covering experimentally. If there's any deviation from, how should I interpret that region? If
Okay.
there's any deviation with respect to standard model physics or anything?
no, this is
No.
just standard model physics.
Just standard model.
This is essentially constraints that we get already. This has been done for the past decade. People have been improving these limits here. It's been going up a little bit.
Okay.
You just, this is being done using this strategy here. So using the current gamma ray data that we have, those constraints were obtained. That line was obtained. But that's only a lower limit. That's the point. You cannot get higher if you don't have enough sensitive enough instruments. That's why you need things like CTA.
That's what I was trying. So go back to the plot then. What I was struggling to understand is how come that's an upper limit and not a lower limit?
No, it's a lower limit.
Sorry, how is it a lower limit and not an upper limit? So if I have a stronger magnetic field, how does it not give you a deviation that you can see more easily? If you understand, I'm sorry if I'm misunderstanding something, but
I think I got your question. Let me see if I got it. Okay. It's a lower limit and not an upper limit because things might happen in between that we are not accounting for. This is a simple model to start with. And also, the point is that our detectors can only observe a given angular size. Whatever happens at a scale smaller than the point spread function of the detector, it's beyond reach of the instrument.
Oh.
That limits what we can do. Right? There are essentially two angular scales that are relevant. So the size of your telescope, the field of view, that tells us that limits on one side. So if your field of view is very tiny, it's just this, you cannot see the whole halo.
okay.
If you are,
So even if the magnetic field is larger, you wouldn't be seeing anything. Is that what you're telling me?
that's the field of view, yeah. And the other one, it's the point spread function that gives you essentially the size of the pixel here. So yeah, it's an interplay of these two quantities.
For question or comment?
Actually, I have one question. Yeah, same figure in the papers. This might be a very elementary question, but for the gamma ray cascades, the slope changes at 10 to minus 1 milliparsec.
That's a good point. Yeah.
And I'd like to know the physics which determines that change.
Yeah, that's a very good point. The physics that determines that change is essentially the physics related to the propagation of electrons in magnetic fields. That change is related to the coherence length, right? It changes here around 10 to the minus 2 megaparsec. So that's about 10 kiloparsec. 10 kiloparsec is more or less the size at which the electrons will start interacting with the CMB. So it's an interplay between the coherence length of the magnetic field and the cooling length of inverse Compton scattering of the electrons.
So,
And of course, the Larmor radius of the electron.
I see. So in the left half, left side,
Yeah.
Random square root n appears. Okay.
Yeah, that's diffusion. That's diffusion. One is the diffusive regime and the other is the ballistic regime. So here it's the ballistic regime because the size of the magnetic field within a scale of 10 kiloparsec or 1 megaparsec, you can imagine that it's just a domain with a homogeneous magnetic field. So that's a ballistic propagation. And here it's a diffusive propagation.
Yeah, I see. Thank you.
Then, no more questions or comments? Okay. Let's say Rafael again.
Thank you very much.
Have you stopped the record?
Okay.